So the research I've been working on for the past few years is neutrino physics. With the KM3net collaboration, we've been building a new detector called KM3net, and this is to measure neutrinos. And with this new detector, we've done basically the first measurement to find neutrino properties. So at CERN, we have these detectors that are in a tunnel underground, but for KM3net, we are building this detector at the bottom of the Mediterranean Sea. And how we're doing that is we have the sea floor, and we deploy these lines that are about 200 meters high for the detector that I'm working on, and they have glass spheres on these lines, and all these glass spheres, they contain light sensors. And with these light sensors, we're building a three-dimensional grid underwater. We want to measure these neutrinos, but they're very hard to measure. But what can happen is a neutrino comes through the water and then hits a water particle in the detector somewhere, like here, and then another particle comes out that's much easier to measure. So you get, for example, a muon that goes in this direction, but this muon will emit light, which will then hit the light sensors, and in that way we can indirectly measure neutrinos. So neutrinos are very hard to measure first and foremost, and that's why we're building such a thing at the bottom of the ocean. And then we want to measure a very specific property of these neutrinos, which is called neutrino oscillations. And what that means is that when you start out with a neutrino and it travels through space, it changes its flavor, what it's called the neutrino flavor. We know these neutrinos have a mass, but we do not know which of the neutrinos is the heaviest. In the standard model of particle physics, neutrinos are actually not completely well understood. They don't really fit into the model properly. That is because in our model they have no mass, but because we see oscillations, they must have mass, because theoretically we can only see oscillations if neutrinos have mass. So this doesn't fit. This is one of the areas where we can still learn a lot about what is missing in our description of the universe. If we can understand neutrinos better, we can understand the universe better. So there's a lot of steps to be made here. We've been measuring for about a year, and we have this data set that has 200 million events. We expect a certain number of events in different parts of the phase space, as it's called, of our detector. And what we see is actually corresponds completely with what the theoretical prediction is, that at some point we see no oscillations, and that's what we expect. In another part we do see oscillations, and we exactly see the oscillations that we were expecting. So in that sense, we understand the detector and we measured exactly the oscillations that we were looking for. The current detector is about 5% of the full detector in terms of size. So we can already see the interesting physics, and the detector will only get bigger. So in that sense, our understanding of neutrinos can only improve from here on out.